Hi everyone. Again, welcome to our Grammarly AI-NLP Club meeting. My name is Vipul Raheja, and I'm an applied research scientist at Grammarly. I'm based in San Francisco, and I'm pleased to moderate today's talk. This talk is part of the Grammarly AI-NLP Club series. It brings together leaders and specialists in AI, machine learning, natural language processing, to share their work and different insights. Before we jump in, I'd like to cover a few event logistics. The first one is about the Q&A session. So please feel free to submit your questions to the Zoom chat during the presentation, and Mina will try to address them either when there are natural breaks or at the end. But you can also ask her anything during the networking session, which will happen after the talk. And so feel free to stay around for that. And more about the networking session. So these events are intended as an opportunity for you to connect with others. So after the talk and Q&A, we are inviting you to chat in a more informal, chilled out setting where you will have a chance to chat with Mina and the Grammarly team. And you can find the link to the networking session in the Zoom chat. So we will be sharing the link to that in the chat. So you're very welcome and encouraged to join and talk to each other and to us in that session. So let's now get to the main part of today's meetup, and I'm thrilled to introduce Mina Lee. Mina is a fifth-year Ph.D. candidate at Stanford University, advised by Professor Percy Liang. Her research interest is to enhance human productivity and creativity in the writing process by understanding human-computer interaction and leveraging natural language processing techniques. So everyone, please welcome Mina Lee.
All right. Hi, everyone. Thank you, Vipul, for a kind introduction. Let me start the slides. So again, my name is Mina Lee, and I'm a PhD student at Stanford University. And today I'll talk about writing with artificial intelligence. And more concretely, I'll give an example of building and evaluating a certain type of writing assistants, as well as understanding the dynamics between the humans and the writing assistants. So why should we care about writing with AI or AI-powered writing assistants? So to this audience, I probably don't need to convince you, but for those who are joining outside of Grammarly, let's talk a little bit about the writing assistants. So the most common form that you might encounter writing assistants in real life is this kind of autocomplete systems. Like whenever you're searching the internet or writing an email or just typing on your phone, these systems are constantly trying to predict what you're typing next or what you're trying to type. So we use these AI-powered writing assistants every day. And in addition to autocomplete systems, a lot of people use more specialized tools, especially for revision. And most of us probably use Grammarly, which provides suggestions and explanations for not only grammar and spelling mistakes, but also style and tone, and so much more. And there are also other tools such as WordTune and ProWriting Aid, etc., which support different sets of functionalities, such as rewriting, shortening or lengthening a sentence, or changing formality of the text. Recently, AI, or more specifically, large language models, improved its capabilities significantly, and it has been used as an ideation tool for writing as well. For those who are not from an NLP background, you can think of language models as a black box that takes in a prompt as an input and then outputs a completion. So in this case, the bolded text, why AI assisted writing, is a prompt, and then a model behind this interface generates this paragraph. And I'll introduce more examples of writing assistants later in this talk. So today I'll present my work in building, evaluating, and understanding AI-powered writing assistants. Concretely, there will be 3 different threads. So the first is about building, and next evaluating, and next one is understanding. And I'll briefly introduce the motivation behind each work and related work and main approach, key ideas, and then takeaways. So let's dive in. So for the first part of the talk, I would encourage you to think about these 3 questions. First, what kind of autocomplete systems have you used? Second, what kind of autocomplete systems are suitable for mobile environments? And third, how would you measure the usefulness of such systems? So this part of the talk is based on this paper titled Learning Autocomplete Systems as a Communication Game. So let's see how we can build a writing assistant. So for simplicity, let's represent this kind of existing autocomplete systems as a square box on the right. And imagine this scenario where you want to type this sentence like as fast as possible. Say that you're running late to a meeting and like you're literally running and then like typing it on your phone. So the intended sentence you want to type is I will be 10 minutes late. So you start typing like I will be, but then it's hard for the system to guess like what you're actually trying to type. It's unclear what the next word should be, for example. So in this case, we can say that the prefix of a sentence fails to capture the meaning of the sentence. But in this case, what if the user types in keywords? For example, instead of typing I will be, the user can type 10 minutes late. And to humans, it's very clear what the user is trying to say. And if humans can predict, then like can we make the system also predict what the user is trying to say? So here the key insight is that the keywords of a sentence could better capture the meaning of the sentence. And we want to build an autocomplete system that can take in this keywords as input and then generate a full sentence. So we consider this task. But then how can we actually build such an autocomplete system? So here is the problem. So there is no such system, hence there are no users. Hence, like you can't just collect the data and then train a model. And if you were to collect the data by telling people, well, imagine there is such system, it will probably result in suboptimal keywords because the user doesn't know like how the system will respond, and real humans have tendency to adapt to the system. So it won't capture such behavior, hence result in like suboptimal data, hence suboptimal autocomplete systems. Since we can't do the supervised learning with kind of like fake data, our approach here was to use unsupervised learning by framing autocomplete task as a communication game. So if you think of users and systems as like 2 agents with 2 different goals, you can view that there are 2 competing goals. One, the user has a goal of writing as little as possible, and 2, the system has a goal of guessing the intended sentence as accurately as possible. So in this communication game, the user and system cooperate, like they have to cooperate to make communication more efficient and accurate. So I mentioned that we're going to use unsupervised learning. So how can we actually do that? We use Encoder-decoder framework. In practice, you can think of like these encoder and decoder as a simple sig-to-sig models. And it's basically like a self-play. So the encoder tries out different combinations of keywords from the sentence and see if the decoder can reconstruct the sentence. And then the decoder getting the keywords and tries to reconstruct the sentence as accurately as possible. And behind this framework, we also use like constrained objective optimization and reinforcement learning so that we can like back propagate through this like discrete keywords. But for more details, please refer to the paper. And with this approach, we built an autocomplete system, in which case is the decoder. So encoder is the user, and the decoder is the autocomplete system that we want to have. And we are going to test out this autocomplete system with real users and see how well it can perform. So here is the interface that we used for the user study. On the left-hand side, we're asking people to enter keywords to make the system generate the target sentence. And when they enter the keywords and press the go button, then the system gives them 3 options. And for each of them, they mark whether it's good or bad. And on the right-hand side, we also ask the same user to type a target sentence so that we can measure the time that it takes to write a full sentence versus the keywords. And the results are as follows. So we see nearly 50% reduction in typing time when they use keyword-based autocomplete systems. You can see that like for keywords, it took like 3.85 seconds. But for typing the entire sentence, they took nearly 6 seconds, while achieving like reasonable level of accuracy, around like 80%. And we also observed that this autocomplete system is robust to different user variation, meaning like different user inputs, like different people may enter different keywords, and you'd expect the system to be robust to that. But then we also acknowledge that there could be possible overhead for choosing keywords and selecting suggestions. So we envision that this kind of autocomplete systems are useful when you're writing a similar sentence like over and over. Maybe you are constantly late for the meeting, and then instead of writing the full sentence, now you know that you can only type like 3 words and get the full sentence. Or you may not care about exactly writing that exact sentence. But so here you can see for the keywords like recommended restaurant, you might be okay with the sentence, I highly recommend this restaurant, but you might be also okay with like, I definitely recommend this restaurant or highly recommend this restaurant. So if like the exact phrasing is not big of a concern, or if you are writing the same sentence over and over, then this autocomplete system can kind of act like a quick macro for you, but more robust than just like manually defining the mapping. So this concludes the building part of the talk, and it's like a simple example of like a different type of autocomplete system that you may not have seen. But yeah, if you were to build such system in an unsupervised way, this could be one way to go about it. I think there is no questions so far. Then I'll move on to the next part. So next part of the talk will be about evaluating writing assistants. Here we are going to specifically look at contextual thesaurus systems. And before jumping into the talk, I want you to consider the word amazing in this sentence. I read an amazing paper today. And say that you have a sentence right before this sentence that also contains the word amazing, and you want to change it up because you don't want to repeat the same word over and over, then how many synonyms can you think of on your own? And are all the synonyms from a thesaurus of your choice like appropriate? So for me, I can think of like I read a great paper, I read cool paper, fascinating paper. I'm not sure what kind of synonyms you're thinking of, but I hope there are some like list of synonyms in your head. All right, so the second part of the talk is based on this paper titled Swords, a benchmark for lexical substitution with improved data coverage and quality. This is a joint work with all these amazing collaborators, and you can download the data set and code from this link. All right, so there are many dictionaries and thesaurus systems that provide a list of synonyms for a given word. So previously, like in 80s, there was like an actual like physical book. And I think they're still like revising or renewing their thesaurus. So back then it was like only physical form of book, but then thesaurus.com digitalized those thesaurus, and a lot of people use this tool to broaden their vocabulary. And nowadays, a lot of dictionaries also show synonyms or antonyms, like in addition to the definition. However, you may notice that some of the synonyms may not work for the context that you're using the word. Because of that, users would have to go through each synonym in the list and judge the appropriateness of that word in their own context. And this is especially challenging for non-native speakers like myself. And recently, many applications were developed to mitigate this problem. So notably, Grammarly, WordTune, and Grammar Coach by thesaurus.com take a word and the sentence that the word is in as context and try to find appropriate synonyms. But then they're still not perfect because they're being selective here. So these systems may leave out a number of other appropriate synonyms. In addition to these commercial systems, I like to challenge you to think of language models as contextual thesaurus systems too. For example, GPT-3, a popular large language model from OpenAI, appears to perform the task pretty well out of the box. So here, the bolded text again is the prompt, and the rest of the text is the completion the model generated. So given one example pair of sentence, target word, and a list of synonyms, the model generates like pretty good set of synonyms, like for the word amazing, like wonderful, astonishing, outstanding, stunning. But then you may have already noticed that the model generates the same word like multiple times, or even lists amazing as one of its synonym for the word amazing, which is not the right thing to do. But assuming that we will post-process this list of synonyms by removing duplicates and etc., how good do you think like GPT-3 or other language models are as contextual thesaurus systems? Or more broadly, how can we evaluate contextual thesaurus systems? So in NLP, this task of finding appropriate synonyms or substitutes given a context and a target word is referred as lexical substitution. And it has been studied like since 2002. To evaluate contextual thesaurus systems, we decided to create a large benchmark for the task. So here is our data collection procedure. So here the target sentence, like the running example, would be my favorite thing about her is her straightforward honesty, and the target word is straightforward. So given this sentence and the word, we first collect a pool of candidates, like synonym candidates for the given context and target word from human annotators. So left-hand side are the words that humans could think of, like off the top of their heads. And we collected that list from 6 humans. And on the right-hand side is the list of synonyms from context insensitive thesaurus. So we use like thesaurus.com, which is based on Roset's thesaurus. So we combine all these synonym candidates into one pool and ask 10 different human annotators whether they think these words can substitute the target word. So we ask, would you actually consider using this substitute in this sentence? And maybe for the word candid, 7 out of 10 people said, yeah, I will use it. And for the word unvarnished, maybe only 5 people said yes. So then we take this final score as an appropriateness score for each synonym candidate. And as a result, we built this benchmark, a test bed called sorts that improves data coverage and quality from previous benchmarks. Our benchmark covers over 1,000 instances of a sentence and target word and contains over 20 synonyms per word. And compared to the previous largest lexical substitution benchmark, it contains like more than 4 times more synonyms, and then 1.5 times more appropriate synonyms. So this is like one example where for the word straightforward, you see a list of words that are ranked based on their appropriateness, judged by 10 human annotators. So it goes like sincere, genuine, frank, candid, direct. And this can be used as a development set and test set to evaluate different contextual thesaurus models or systems. So talking about evaluation, to briefly go over the evaluation setup, you can consider 2 settings. One is generative setting and the other one is ranking setting. So for generative setting, each system is given with context, like the sentence and target word. And their job is to first generate substitutes and then rank them based on their appropriateness. And for the ranking setting, each system gets not only context and target word, but they also get a list of possible substitutes. And their role is just to rank those substitutes based on the appropriateness. And for the interest of time, I'll just go over the generative settings results and leave the ranking setting to the paper. And for the metric, since we care both precision and recall, we report F1 score for the top 10 substitutes here, but you can increase like the number of synonyms to match with, you know, like whatever your system's users' needs are. So here are the results. In the table, the first row is the performance of thesaurus.com. So if you take the list of synonyms from this website and use that as a ranked substitute, then this would be the score that you will get. So this could be considered as a baseline that everyone, if like everyone uses thesaurus.com. And the second row represents the performance of like human memory, basically. So if a human has to write down a list of synonyms off the top of their heads, then this would be the score that they will get. And the human judgment can be considered as the upper bound of this task. So we basically repeated the data collection procedure with a disjoint set of human annotators and compared like inter-annotator like agreement. And this is what you will get from the like 10 humans judgment scores. So given this lower bound and upper bound, let's look at the performance of 4 different systems, GPT-3, WordTune, and BERT-based lexical substitution, which was like the state-of-the-art model back then, and just basic BART. And a 2-liner takeaway is that all systems perform worse than human judgment, which is expected. But interestingly, GPT-3 and WordTune perform better than human memory, which indicates although these models' performance is not perfect, it doesn't match human judgment performance, but it still can already provide some help if humans are operating by themselves. So if they're struggling to come up with different words by themselves, then these models could provide some kind of inspiration. So we briefly looked at a specific type of writing assistant here, namely contextual thesaurus systems, and looked at how we evaluated these systems. So that concludes the second part of the talk. Is there any questions?
If there are no questions from the audience, I'm happy to ask one.
Okay.
This is awesome. The goal here is to diversify a writer's, writing or expand their vocabulary and provide them with new ways to phrase things. And this is just the beginning because we are making changes at a word level, but taking a step further, if we want to make changes, if we want to build a system that can make changes to phrases or even like syntactic changes, I'm curious to know your thoughts on evaluating those kinds of things.
Yeah. So yeah, it could be word level and phrase level and sentence level, and I guess it can be even like paraphrase level. And I guess the thing we realized by working on this project is that even like when you look at word level, like evaluating whether it's like appropriate substitution or not was pretty difficult. So maybe one behind story I can tell is that the reason why we chose to do this binary labeling as opposed to, like we could consider different axes for the synonyms. I think there is a huge literature on like near synonymy, and it describes, like 10 or like, dozens of different dimensions that like 2 words can be similar, but then also different. Like they might differ in terms of like attitude, like maybe one is slightly more favorable and the other one is more like neutral, and they might also differ in formality while like all like similar in the meaning. So yeah, that's why we kind of like, for the practical reason, we chose to just go with binary, but then have more people evaluate the appropriateness of these synonyms. So yeah, I feel like it's gonna be even harder to evaluate like phrases and sentences, and it'll be also very subjective.
Yeah.
So yeah, it's kind of hard to imagine like how it could be done, and like whether this would be extendable to cover those. But yeah, I think that is an active like research area.
Yeah, I mean, of course. I think this point you mentioned about all these different dimensions also is interesting, because I think the binary decision, for the sake of simplicity, encompasses all of those, now that I think about it, because there could be, is the meaning preserved, or is this just a more diverse way to say the same, convey the same sentiment, and so on. So yeah, that's really interesting. Yeah, thank you. I think we can continue.
Okay.
Yeah.
All right. And then I'll move on to the third part of the talk, which is about understanding. So instead of posing 3 questions or 2 questions for this part, let me motivate our work by sharing some of our recent observations about human AI collaborative writing. So in the past few years, I saw more and more cases of people using AI, specifically language models. And I showed this like screenshot earlier, which is the playground built by OpenAI, in which you can explore like different versions of GPT-3 with different coding parameters. And I guess to my surprise, this tool was not only used by researchers or developers, but also by professional writers. So to show you concrete examples, one writer wrote a book with GPT-3 in 24 hours, like last year. And after that, there have been a number of books written with GPT-3, and like GPT-3 is even listed as one of the co-authors. And this year, there is even an essay that won Best American Essays Award that was written with GPT-3. So from these examples, it is pretty clear that these models have a lot of potential to help our writing process. And using this technology, many startups developed tools for specific domains, for example, copywriting. But the thing is, they share like demos and user testimonies to demonstrate the helpfulness of AI in this like writing process, maybe specifically for copywriting or email writing. And sometimes they even claim that like with their tools, like you can write the text like 10 times faster. However, it's unclear how we can validate these claims and understand how AI is helping humans write in a systematic way, not just testimonials. That's what motivated us to work on understanding the human AI collaborative writing process. So this part of the talk is based on this paper, co-author designing a human AI collaborative writing dataset for exploring language model capabilities. So to understand language models' capabilities, there are at least 2 challenges. So the first one is the language model capabilities are highly context dependent. So depending on the domains or topics, or even like exact phrasing of the topic or question, and like users' writing style, the language models can demonstrate like really different performance. So here, I'm showing an example of GPT-3's performance on 57 different domains. So you can see that like the model performs really well for, say, like US foreign policy, but then when it's asked about like college chemistry, then it does like pretty poorly, almost like a random chance. So how can we reason about like these language models' capabilities when we expect these models to deal with like these varying contexts? And secondly, language model capabilities are often subjectively interpreted. So even if we consider the same piece of text, some people may want new creative ideas, whereas the others may want more coherent, predictable conclusions from the system. So based on these different goals and interests, the assessment of the same text or interaction or assistance could be different. So with these challenges in mind, like how can we better understand language model capabilities in various contexts in a holistic manner, while allowing subjective interpretation in situated environments? And our approach is to curate and analyze large interaction data sets. We propose 4 desiderata for designing large interaction data sets. We exemplified this approach and designed CoAuthor to capture GPT-3's capabilities. But before going over these desiderata, let's first take a look at the interface and what kind of data we collected first. So this is the interface that we use. So it was basically a text editor initialized with a writing prompt. And to interact with the system, you just press the tab key whenever you want suggestions, and the system will show you 5 suggestions. And you can navigate these using your arrow keys or mouse and select one, which will append that suggestion to your existing text. And then you can edit that suggestion, or you can keep querying the system until you find, satisfying ideas. And for the model, we use GPT-3 without any fine tuning or prompting. And we only change just the temperature and frequency penalty to change the randomness of the suggestions. So here are the examples of suggestions under high randomness and low randomness. And we looked at 2 types of writing, like creative writing and argumentative writing. So notice that under low randomness, all the suggestions look kind of alike, whereas under high randomness, you get more diverse set of suggestions. And this is what you will see from each writing session. So the user started with a prompt and query the system if you want suggestions, and you just like look through them and pick the one that you like and maybe edit it around to make the story more coherent and continue writing. So now let's briefly go over each desideratum and see how we reflected it in the design of CoAuthor. So to cover diverse contexts, we looked at multiple types of writing and writing prompts and writers. So in the data set of CoAuthor, you will find stories, like over 800 stories for creative writing written by like almost 60 writers, and over 600 essays written by 49 writers. And we used 20 different prompts so that it's easy for them to get started. And then also it will allow us to compare different stories and essays written for the same prompt. And we grabbed these prompts from like the subreddit writing prompts and one of the article from the New York Times that lists up like a bunch of topics for the argumentative writing. And in total, we had 63 qualified crowd workers from Amazon Mechanical Turk as our participants. And in order to support subjective interpretations, we kept the raw writing outcomes and writer perception, which we got from the survey after they finish each writing session. But we did not make any judgment about the final story or essay they wrote or the survey responses. So it's all up to the designers who want to use CoAuthor to decide whether this behavior of this user or this outcome or like these certain features in the final stories are desirable or not. And the most importantly, CoAuthor captures processes, not just results from the writing session. So we collected basically every keystroke in every event in the text editor, including like cursor forward, cursor backward, text insert, text delete, suggestion get, open, close, up and down. And we also stored timestamps along with those events so that we can precisely replay each writing session in our interface. We did that because we believe that understanding the writing process is as important as understanding, like the outcome of the human AI collaborative writing. And lastly, we designed CoAuthor so that it will allow possible reuse and expansion. You're probably already familiar with all these like new large language models that came even after like GPT-3, and there are new models like every month or even like shorter than that. And it's really hard to reason about all these models, while for each model, you can also change different decoding parameters and consider different contexts. So the space that we need to explore to fully understand like large language models capabilities in this interactive like setting is just so vast. So our hope was that by using like general purpose and standardized format, we can all share our data and then contribute to building the general understanding and knowledge around this space. So everything is public and shared. So if you go to this URL, you'll find that there is a list of replayable like writing sessions that we collected. And these are some basic stats. So in each session, each user interacted with GPT-3 for about 10 minutes and wrote about like 400 word long stories and essays and queried GPT-3 around like 12 times. And so feel free to go explore, and we encourage you to critique and expand this data set like however you want and need. And now let me share some of the initial analysis results we had in the paper. So there are like so many things we can explore with this rich data, which I'll also cover it later. But here are some like first initial steps towards understanding different capabilities of language models. So first, we looked at language capabilities. And we asked the question, can GPT-3 generate fluent text in interactive settings? So first we looked at grammaticality. We used a like existing Python library to identify grammatical or spelling errors. And the result was that for the sentences written by both the human writer and GPT-3, which means like the human probably selected suggestion from the system and then edited it afterwards, had the lowest, like smallest number of errors compared to the sentences written only by the writer or the sentences only written by GPT-3. And then we also looked at diversity of vocabulary, and the trend was the opposite. So for the sentences written by both the human writer and GPT-3, the diversity of the vocabulary was the highest compared to the other two, which may indicate that like GPT-3 is or can be helpful to expand the user's vocabulary, which we also saw from like the SWORD's evaluation as well. And secondly, we looked at ideation capability of language models. And we were curious whether GPT-3 can contribute new ideas to writers' stories and essays. And here I'm mainly presenting the results from the story writing. And what we did to identify new ideas was pretty simple and straightforward. So because it's hard to like precisely identify all the cases that GPT-3 contributed new ideas or provided new inspirations, we took a conservative approach and identified only like the named entities, which are just like names and places and etc. So in this example, Dr. John would be an example of a named entity that was first written and suggested by the model. So it didn't exist in the previous context. And we look at the following context and see whether that new named entity was reused by the human writer or not. And in this case, I think we can pretty safely say that, okay, the model came up with a new name or a new place. So that is pretty safe to consider that, okay, the model did contribute for the ideation. So with that approach, we observed that 13% of all the suggestions contained new named entities. And among those, the writers reused 20% of the suggested new named entities. So we see some evidence that like these models do have some ideation capabilities, but this is of course like very limited sense of ideation. Okay, lastly, we looked at collaboration capability of language models. So does the randomness of GPT-3 influence collaboration? And here we defined two metrics, like equality and mutuality. And equality represents like how evenly a writer and GPT-3 distributed turns. So when we aggregated the score across all the prompts and writers and only look at the GPT-3 with low randomness and GPT-3 with high randomness, we didn't see much difference. But when you break it down by prompts, which are the leftmost and the middle plots, then you see some difference. So for some prompts, like the GPT-3 with low randomness have higher equality, but for the other prompts, it's the opposite. And when you break it down by writers, then you see even greater difference. So from this, we can infer that collaboration capability depends on the context, as well as like the writer's preference. So some writers may prefer to get the suggestions that are more predictable, more coherent, whereas some writers may prefer to get suggestions that are more creative and more unpredictable. And the same trend holds for mutuality, which represents the amount of interaction a writer has with GPT-3. All right, so beyond this, we also show that designers or developers can use CoAuthor to formulate hypotheses under various definitions of good writing and collaboration. But for the interest of the time, I'll skip over this and maybe talk about different ways that one can use CoAuthor briefly. So some people might be interested in using CoAuthor to study novelty effects or longitudinal change. For example, do writers learn to leverage GPT-3 better over time? Because we have a pool of writers who interacted with 2 versions of GPT-3 many times, like up to 60 times, I think, we can reason about this change over time. And on the linguistic side, we could also reason about like accommodation. How does the style, voice, or tone of a writer or GPT-3 influence that of the other over time? Is the influence unidirectional or bidirectional? And more from an NLP angle, we can also look at the edits made by human on the GPT-3 generations and maybe use that to learn like an editing tool that will mimic human preference like much better. So that concludes the third part of the talk. So today we looked at building a specific kind of autocomplete system, namely keyword-based autocomplete system with a simple like sig-to-sig model. And in the second part of the talk, we looked at evaluating contextual thesaurus systems, not just commercial ones, but also language models as thesaurus systems. And in the third part of the talk, we talked about like understanding human AI collaborative writing by designing this large interaction data set. And I shared some initial analysis that you can reason about like different capabilities of language models. So if you have any questions or feedback, I really appreciate it. Thank you.
Thank you so much, Mina. What an amazing talk.